Hello and welcome to this video for CE108 Mechanics of Deformable Solids. We're still in chapter 7, bending chapter. And so what we have seen so far is how in terms of the external loads or the external moments that are applied to a beam that is subjected to bending, how based on this we can calculate the internal shear and the internal moment within this beam. So this is what you can get using the integration method. In this case, the internal shear, internal moment only depends on the external shear and the external moment that are applied to this beam. Now, if you want to calculate the stress that is acting within this beam, so the stress will tell you the risk of fracture, then not only you need to know the internal shear, internal moment, but you need to know a second thing, which is in this case the geometry of the member. And specifically in that case, the geometrical feature that matters the most for bending is the moment of inertia IZ. In this case, you need to know both the moment of inertia and the stress. For example, to calculate the normal stress, you need to know the internal moment and divided by the moment of inertia. So those two information, the geometry and the loads, are both important. So what we are going to see in this video now is how to calculate the deformation, the actual deformation. And in this case, the deformation of a beam is going to be dictated by its deflection. The deformation in the case of a bending problem is the deflection of the beam, the lateral deflection of the beam. So in this case, when you want to calculate the deflection, so first you will need to know the internal load. The internal load will dictate how much deflection you have. You will also need to know the geometry of the system, the geometry of the member, and specifically its moment of inertia will also be important and will have an effect on the propensity of this member to exhibit some deformation, some deflection when it's subjected to bending. But when it comes to the deformation, there's going to be a last property that we need to know, which is that irrespectively of what are the loads that are applied to this beam and irrespectively of what is the geometry of this beam and its moment of inertia, we need to know one last information, which is what is the beam made of? What is the material property? What is the material that this beam is made of? And specifically, what will matter is what is the stiffness of this material. If you have a material that is very stiff, then it's going to have less deformation than the material that is very soft. So in this case, the stiffness and specifically the Young's modulus is also going to be important to determine the deformation of these materials. So when it comes to the deformation, you will need to know those three things. You will need to know the geometry and the moment of inertia. You will need to know the internal shear, internal moment, but you also need to know what is the stiffness of the material that the beam is made of. And based on those three information, you will be able to calculate the deflection of a beam that is subjected to bending. So the first thing is, what do we mean by deflection? So for this, let's take an example. Let's consider a beam like this. And let's assume that this beam is attached to a pin at a given position and then a roller at another position. And then this beam is subjected to a given load like this, a shear load. And so let's assume that this is the shape of this beam before deformation. So now the question is, what is going to be the deformation of this beam after the effect of the load is applied? So after the deformation, when you have a beam that is subjected to bending, the beam used to be a straight line before deformation, and after the deformation, the effect of the bending is going to change the beam not into a straight line anymore, but into a curve. So now, after the deformation, the beam is going to become a curve and will look like something like this, for example, where in this case, the effect of the shear load that is applied at the right extremity of the beam is going to be to induce a deflection, where in this case the deflection is that the beam is not a straight line anymore, it's now a curve. So now we need to think how we're going to quantify this deformation. And so when you think about, when you compare the position of the beam before and after deformation, the effect of the bending is that for some part of the beam, some part of the beam will move up, some part of the beams will move down. The effect of the bending is not going to displace some elements of the beam right or left. It's only going to move some part of the beam up, some part of the beam will move down, due to the fact that the straight line, that's what the beam used to be, a straight line, and now it becomes a curve with a certain curvature. So the deflection will correspond to a lateral displacement of the beam, where at each position of along the x-axis, each point M that is located at a given position x will either move up or move down due to the bending. And so to quantify the extent of bending, what we typically use is the elastic curve of the beam, where the elastic curve is the deflection curve. It's the curve that passes through the centroid of each of the cross section. So the elastic curve is the curve that, when you consider the beam, for each position x within this beam, you will define the curve that goes through the centroid of each of the cross section. So initially, this elastic curve is a straight line, and then you look at how this elastic curve that again goes through the centroid of each of the cross section of the beam becomes deformed after the deformation. And so what you can draw then to characterize the extent of the deformation is to draw the value of this elastic curve. So you can define a function, v of x, that defines this elastic curve, where v of x will correspond here to the lateral displacement of the elastic curve before and after deformation. So you have the elastic curve that I can draw like this. So this would be, in this case, the elastic curve. And if you plot this curve as a function of x, then that gives you a function where at each point, the lateral displacement of the beam, the lateral displacement of the elastic curve, is characterized by a function v of x. So that gives you a function that will allow you to characterize what is the lateral displacement, what is the deflection of the beam at each point x. So for example, if you have your beam going between x equals 0 to x equals L, then what you can do is to plot the value of the deflection, the value of the lateral displacement of the elastic curve between 0 and L. That gives you a function v of x, and this function v of x is what we will use to quantify the deflection of a beam. So when it comes to describing this elastic curve, there is really three geometrical features of this elastic curve that will matter. So the first thing is the value of the function itself. So if you take the value of this function v at a given x, then it's giving you the lateral displacement of the beam at a given position x. So this gives you the amount of deflection that you have at a given position. And for example, this deflection necessarily is going to be equal to 0 when the beam is attached to a beam or a roller at this position here. And so this gives you how laterally how much the beam is displaced. So that's the deflection of the beam. That's the function itself. The second feature that will be important is the slope of this elastic curve. So if you calculate the derivative of the deflection, the derivative of v as a function of x, this is what is going to give you the slope. So if you take, for example, a given elastic curve like this, where you plot the evolution of the deflection v as a function of x, then at each point x, you can define what is the slope that the beam is making with respect to the y-axis. So this you can, for example, characterize it with an angle theta. And in this case, if the angle is small and is expressed in radians, then the derivative of the function is equal to the tangent of theta at this position x, and if theta is very small, then you can approximate that the tangent of theta is approximately equal to theta. So this, the derivative of v, gives you the slope of the elastic curve. And so why is it important? Because in certain cases, for example, if you have a beam that is attached to a fixed support like this, then necessarily, because the fixed support prevents the rotation of the beam at the point at which it is attached to the fixed support, then necessarily at the point at which a beam is attached to a fixed support, then the slope is going to be 0 at this point because the beam is attached to the fixed support and cannot rotate. So the slope is also going to be an important feature that describes the deflection of a beam subjected to bending. And then the last feature that will be important is going to be the curvature of the beam. Is the beam concave up or concave down, concave or convex? This is going to be another important feature. That's the curvature. So we already talked a little bit about the curvature of a beam, and one way to quantify the curvature is that if you have an elastic curve like this, so if you plot the function v, if you want to know the value of the function, you just have to look at the value of v at a given x. If you want to know the slope, then you just have to take the derivative. But now if you want to know not the slope, not the value of the function, but the curvature. So for example, in this case, that would be an example of a beam that has a positive curvature with a beam that becomes concave. A beam that becomes convex. Then the question is, how do we characterize how much concave or how much convex the beam becomes? And so one way to do this is, for example, if you want to know the curvature at a given position x, is that you look at this position, the curvature of the beam, and based on this, you can assume that the beam is roughly equivalent to a circle, and then you can define the radius of this circle. So this radius here, the radius of curvature, is what we defined in the previous video, and this radius tells you how curved the beam is, in the sense that if you have a beam with a very large radius of curvature, then the beam is almost straight. But on the other hand, if this radius becomes very small, then the smaller the radius of curvature becomes, the more curved the beam becomes. And in this case, another way to quantify this curvature is also to calculate the second derivative of the function. The first derivative gives you the slope. The second derivative will tell you how curved the beam is. The higher is the second derivative, the more curved the beam becomes. And on the other hand, if the second derivative is 0, then it means that you have locally an inflection point where there is a 0 curvature. So this is only valid for when the deformation are small, in the case of the small deflection. But when deflection are fairly small, then what you can write is that the second derivative of the v function is almost equal to the inverse of its radius of curvature. And this will tell you the curvature of the beam. So if the second derivative becomes larger, then it means that the beam becomes more convex. And so this is what we are going to use to describe the curvature of a beam. We are going to simply to calculate the second derivative of the deflection function v. So we have three geometrical quantities that matters to describe the deflection of a beam. So first we have the deflection itself. We have the slope of the beam, the slope that it's making with respect to the horizontal axis. And then we have the curvature of the beam. Is it concave or convex? So for this, we need to agree on what we will use as a sign convention, what will be a positive or a negative slope, what will be a positive and a negative curvature. So in the case of the deflection, then the sign convention is pretty straightforward, is that when you plot the deflection v of the function, if the beam due to the deflection is moving up, so for example, if you plot the deflection like this and the beam is moving up like this, then this is what we will call a positive deflection. That's a case where V is higher than the x-axis, so that's going to be a positive deflection. On the other hand, if the beam is moving down like this, so at a given x, like so, this is going to depend on x. Potentially the beam can be moving up and moving down as a function of x, but for at a given x, if the value of the deflection is negative, then that's going to be a case of a negative deflection at this point. Now, when we think about the slope, again, there's potentially two cases where first you have a beam that can have a positive slope or a negative slope. So for example, something like this. So in this case, the sign convention that we will be using is for a given x, if the function has a positive derivative, so if the angle that it's making with respect to the horizontal axis is like this, if it's with an anti-clockwise direction, then this is what we will call a positive slope or a positive derivative for the beam at this point. So this is going to be a positive slope. On the other hand, if the beam is making an angle like this with respect to the horizontal axis, which is clockwise, then this is what we will use as the negative sign convention. So this is going to correspond to a negative derivative of the beam, of the deflection of the beam at a given point. Now, when it comes to the curvature, so again, we need to consider two potential cases where the beam can either have a convex shape like this or a concave shape like this. So in all those cases, I'm plotting the same deflection function here. And so now when it comes to the curvature, what we will use for as a sign convention is that whenever the beam is like this with a convex shape where the radius of curvature would be positive, then in this case, this is what we will use as a sign convention to be a positive curvature. The second derivative of the function would be positive. The function would be minimum at this position x in this case. So that's going to give you a positive curvature. So that's a positive second derivative. On the other hand, if the function has a concave shape like this, so this means that you would have a negative second derivative. That would be a local maximum for the function. And so that would also correspond to a negative radius of curvature. So that's the sign convention that we will be using for deflection, slope, and curvature. So now the question is, how do you calculate the deflection? How do you calculate the deflection V of a curve? So for this, we can reuse one of the previous expression that we derived in some of the previous videos. So in the video on the stress, the way we calculated the stress formula for a beam subjected to bending is that we first calculated the strain, and of course the strain is going to be very closely related to the deformation of the beam. So what we showed for a beam that is subjected to bending is that the normal strain of a beam at a given point is given by minus y divided by rho, where rho is the curvature, the radius of curvature of the beam. Where in this case, the y dictates for a given beam, if you have a given beam like this, so you have the neutral surface, and for a given point M, y is the distance from the neutral surface. And in this case, so this relationship minus y over rho gives you the normal strain at a given point M within this beam, which depends both on x at the position x at which you are located, but also on y, that is to say the height of the point within the beam. So then we have, based on this, we calculated the normal stress. And so the normal stress necessarily is equal to the Young's modulus times the strain. So that gives you an expression for the normal strain as being minus EY over rho. But on the other hand, we also derived the relationship that gives you the strain. We derived the deflecture formula. The deflecture formula tells you that the strain at a given point, the normal stress at a given point, is equal to minus y times the internal moment divided by Iz. So this is the deflecture formula that allows you to calculate the normal stress at a given point in terms of the internal moment and the moment of inertia Iz. So now we have two different expressions for the normal strain. We have one expression that comes from the Hooke's law, and we have one expression that comes from the deflector formula. So we can combine those two expressions and say necessarily those two expressions must be equal to each other. So that tells you that if you remove the minus sign, so EY divided by rho, this has to be equal to y times mx divided by Iz. So that gives you an expression based on the fact that those two types of normal stress must be equal to each other. And so this gives us an expression that we can use to calculate the curvature of the beam. Why? Because so what we want here is this, so the curvature of the beam. So the curvature of the beam, this is the second derivative of the beam, and we said previously that this second derivative is the inverse of the radius of curvature. So based on this, we can isolate 1 over rho, and that gives you an expression for the curvature of the beam, the second derivative of the deflection, as being so the moment m. So the y disappear in this expression here. So, and all you get is a moment divided by the moment of inertia divided by the Young's modulus. So this expression here is an expression that gives you the curvature of the beam. It's telling you that the internal moment m is going to dictate the curvature of the beam. So if you know the internal moment, you divide it by the Young's modulus and the moment of inertia, then that gives you the curvature. So this is the moment curvature relationship. It's telling you that the moment of the internal moment within the beam will tell you the curvature. So in terms of the sign convention that we will use for this relationship, those are the same as the sign convention that we use for the curvature. If you have a smiley beam like this, so this is what we said would be a positive internal moment, and so that also corresponds to a positive curvature. So the second derivative of the beam is going to be positive. And on the other hand, if you have a sad face like this, then this is going to correspond to the negative sign convention, where at this point the internal moment would become negative, and that would also correspond to a second derivative that is negative. So that would correspond to a beam that has a concave shape with a negative curvature. So now the question is, based on this, how are you going to calculate the deflection of a beam? So ultimately what we want is the deflection of the beam. So we want the function v of x. That's what the ultimate goal of what we want. So the way you are going to do this is by using again the integration method, just like what we saw previously. So how is it going to work in practice? So the way it's going to work is that you when you face a bending problem, the first thing is that you will always know what is the distributed load, the vertical distributed load that is applied on this beam. And as we saw previously, if you integrate this distributed load one time, then you get the internal shear by using the fact that the distributed load is the derivative of the internal shear. So if you integrate one time, you get the internal shear. Then if you integrate one more time, then you get the internal moment based on the fact that the internal shear is the derivative of the moment at each point of the beam. So now, based on what we saw that if you have the internal moment, the moment is related to the deflection. What we saw is this moment curvature formula. The moment curvature formula that we just saw is a function that is a relationship that relates the moment to the curvature. So the relationship that we just saw, if I rewrite it, is that the Young's modulus times the moment of inertia times the second derivative of the deflection is equal to the moment of the internal moment within the beam. So that's the relationship that we just derived. So this relationship gives you a link between the internal moment and the deflection. And so the deflection here is the second derivative, is the moment is the second derivative of the deflection. So that means that if you get the moment, if you integrate this moment 2 times, then you can get the deflection. So the way it's going to work in practice, since we also know that on the other hand, the first derivative of the deflection at a given x is equal to its angle. So if you multiply this expression by EI on both sides, then it means that if you integrate 1 time the moment, so if you integrate 2 times the moment, what you get is the EI times the deflection V. But if you integrate just 1 time the moment, what you get is going to be EI times the slope. So if you integrate 2 times the moment, you will get the deflection, since the deflection is the second, the moment is the second derivative of the deflection. But on the other hand, if you integrate just 1 time the moment, then you get the slope. And then the last thing is that if you integrate the slope, then you will get the deflection. So another way of saying that is that you can go the other way around, is that if you take the product of EI times the deflection, if you differentiate that, if you take the derivative of the deflection, then you will get the slope. The slope is the derivative of the deflection. So this is when you differentiate, while on the other hand, the other direction is when you integrate. So if you differentiate the deflection, you get the slope. And now if you differentiate the slope, then you would get the moment, or on the other way. So if you differentiate 2 times the deflection, then you get the moment, since the moment is equal to the second derivative of the deflection. And on the other hand, so if you redifferentiate the moment, you get the internal shear. And if you differentiate the internal shear, you get the distributed load. So in practice, if you want to calculate the deflection, which is usually the goal, then it means that you will need to do 1, 2, 3, and 4 successive integration. You will need to integrate 4 times the distributed load in order to find the deflection. So for this, the general method that you will need to follow in order to find the deflection of a curve subjected to bending is that it's going to be fairly similar to the integration method that we previously saw. The first thing is that since you will need to do 4 integration, you will get some integration constant. And to find those integration constant, you will need to use the limit condition. So the first thing will always to find the limit conditions. So those limit condition can be what is the value of the internal shear, what is the value of the moment, what is the value of the slope, or what is the value of the deflection at the 2 edges of the curve of the beam. So the second thing that will also be useful is to identify where there are some discontinuities or some continuities. So you will need to identify some continuity conditions. So if you have some beams that are attached to each other, or if you have some discontinuity in the internal shear and the internal moment, then that will be some other useful information that you can use to find the integration constant. Then the third step is that you will need to integrate 4 times the distributed load. So you will need to integrate W 4 times to get the shear, moment, slope, and eventually what you will want is after 4 integration, you will get the internal shear. You will get the deflection V. And in this case, every time you integrate, you get one integration constant. So you will need to use the limit condition and the continuity condition to find the values of the integration constant. So to find the values of all the integration constants that you got when you integrated 4 times the distributed loads. So once you have this, so you will have, by integrating 4 times the distributed load, you will have all you need. You will have all the internal shear V, internal moment, you will have the slope, and eventually you will have the deflection V, which tells you the deformation, the lateral deformation of the beam subjected to bending. So this is the method that we are going to use to calculate this deflection, to calculate the actual deformation of the beam that is subjected to bending. And for this, again, the things that will matter is, first, what are the external load, external distributed load, external shear, external moment that are applied to the beam, because this is what will dictate the value of the internal shear and internal moment. You also need some information about the geometry of the beam to get the moment of inertia, and you need to know the material that the beam is made of to get the stiffness of the beam, to get its Young's modulus. And all those 3 things, geometry, stiffness, and external loads, will be have an influence on the value of the deflection of the beam.